Now, so far, I've been referencing that in order to find a derivative, we need to take the limit of the difference quotient to solve it. But I also have been saying that there are shortcuts for calculating derivatives to make our life a lot easier so that we don't have to do a lot of this algebra every time in order to solve derivatives. And so the key principles behind this lecture are what are some of those shortcuts or techniques. And basically, we just refer to these as differentiation techniques, shortcuts, whatever you want to call them. So what I wanted to work through is, what are some of those rules and how do we solve derivatives using our shortcuts instead? But if you're ever unsure of a derivative, you can always check it by the long way or by the definition of the difference quotient. So I'll give you a few examples here to warm up with, and actually we'll use those in our table for calculating for examining power. So the first rule that we're going to cover is referred to as the power rule. The power rule is a super awesome shortcut for dealing with what we call power functions. Basically, if you ever have x to the power of k or n or whatever, it will always work for such case. Basically, polynomials. Anytime you have a polynomial, you can use the power rule to find the derivative of it. And in order to examine the power rule, let's look at some of the examples that we've already looked at. We found the derivative of x by itself, which since that was linear, we came up with a derivative of simply 1. So we'll go ahead and write that out. F prime of x here was equal to 1. We also did x squared in our live class. We got the derivative was 2x. We did x cubed a couple videos ago, which we got the derivative of 3x squared. We haven't done x to the fourth yet. Let's actually go ahead and do that really quickly. We have not done the square root of x either, but we actually did 1 over x again in one of our previous videos, and we got the derivative there was equal to negative 1 over x squared. So let's go ahead and look at, actually, I'll let you pause the video, try them yourself, and I'll go ahead and just write the answers here. The derivative of x to the fourth power is equal to 4x cubed. And again, you can go ahead and check that for yourself. And the derivative of the square root of x is equal to negative 1 over 2 root x. Actually, let me make sure I did this right in my head. Actually, no, this should be positive. Sorry, positive 1 over 2 root x. 1 half, subtract 1. Yeah. And we will talk about how I figured that out here shortly after we talk about the power rule. And this one, the algebra behind this, if you're stuck, we can talk about this one in office hours or something if you want to know how to get from here to here. Sorry, this is the derivative. Forgot to write my primes there. But yeah, go ahead and try them for yourself. And if you have trouble, we can work on them together. But anyways, the derivative of those functions are right there. Okay, so here's the question. Is there a pattern here? Do we see a pattern behind these derivatives? And actually, what you'll notice if you look at, say, x squared, x cubed, x to the fourth, the derivatives always have one less power than the original function. And basically, also notice that the coefficient out front matches the prior power to the original function. So here I had x squared, here the coefficient is 2. Here I had x cubed, the coefficient was 3. Here at x to the fourth, the coefficient was 4. And that is the power rule. Basically, that pattern is not a coincidence. That will apply to any polynomial function of any power. And actually, it doesn't just work for whole number powers either. It actually also works for fractions, negatives. Actually, there is one case when it doesn't work, when the exponent is 0, which actually I need to amend this power rule as it says right here, assuming k does not equal 0. But it works everywhere else. But actually, if you're thinking about what about the, you might be thinking to yourself, okay, 1 over x and the square root of x, those don't really look like these other ones. Why do these have anything to do with this pattern or this technique that I'm talking about? Well, actually, we can rewrite these using powers, and you'll see that they also follow in line with the power rule as well. So 1 over x, that's the same as x to the minus 1 power, right? Because the reciprocal is equal to a negative exponent. And 1/2, Another thing you'll remember from algebra is the square root of x is equal to x to the 1/2 power, or basically the nth root of a number x is always equal to the 1 divided by n power. And actually, if you apply that same sort of logic, let's go ahead and look at the power rule. And basically, this always applies if our function is what's called a power function. If it's x to a power. Notice that x needs to be in the bottom. If x is in the top, this rule does not work, a very common mistake. But what it says is that if f of x is equal to x to the k power, where k is any real number except for 0, then f prime of x, the derivative will always be equal to k times x to the power of k minus 1. Or another way of saying this is you write the power out front and then you take away 1. The way that I often say this is, in order to take the derivative of a function, you drop the power and subtract it by 1. And also, this brings up another point. There's actually a lot of different ways to write derivatives. So far in our lecture videos, in our notes, I've always referred to derivatives by the notation f prime of x. But another common way that you'll see it in the next few pages of our lecture notes is d dx or dy dx. So it's important to note that Leibniz notation, basically, we often refer to as the prime notation f prime as Newtonian or Newton notation. And actually, he did something differently as well. Sorry, I misspoke there. We refer to this as function notation. Newton used I believe he used a dot above the number. He was he wasn't just a physicist, but one of his primary interests was physics, and that notation is actually more prevalent in physics as opposed to math, and we won't be really using that notation very often, but sometimes derivatives are written by putting a little dot over the variable like so. But anyways, another notation that we will be using is sometimes d dx, or dy dx. Basically, d dx, what this means is d dx is sometimes referred to as the differential operator, or how you can remember it as meaning, this means take the derivative of whatever follows. And basically, the ratio of d to d is sort of like a cancellation, meaning where d refers to derivative. And dx on the bottom is sometimes called a differential. We'll talk more about what that means later. For now, we'll skip over the intuition behind it. But basically, this means take the derivative of the function with respect to x. And we need the dx on the bottom, which tells us, okay, what variable are we using? Because sometimes you need to take a derivative d dy, d dz of a different variable. And that, is kind of important to know. Whereas if you're using the f prime notation, it's always implied to be derivative of the variable within the function. And so this is before I move on, this equivalency d dx of f of x, this means take the derivative of f of x, and that's equivalent to f prime. These mean the same things. Or another way we might write it is dy dx. dy dx means take the derivative of y with respect to x. And remember, a function is, it's equivalent to writing it in the form y. So this is equal to, you could also think about this as d dx of y, means take the derivative of an equation or function, which is also equal to this, assuming that the equation y is a function. And oftentimes we just write that simplified as dy dx. Basically, summary, there's a lot of different ways to write a derivative. So it's also a more compact way of writing it. And if you look at some of the next examples, it says, you notice d dx is everywhere. Well, d dx always just means take the derivative. And so, let's practice using the power rule, and we'll do this more in the next video. But basically, revisiting the power rule, in order to find the derivative of a power function, you drop the coefficient and subtract 1 from the exponent. So basically here, the derivative of x squared, by using the power rule, k is the exponent. I'm going to write k out front. And the derivative is always equal to k times x to the k minus 1. So k is again 2, so that would be 2 minus 1. Or essentially, I drop the power out front and I take away 1 from the exponent. That will leave me with 2 times x to the first, or 2x. And notice what I get is the same as the derivative we got when we did it via the difference quotient. So again, we did this in class this week. Let's go back over that math. It's right here. Notice it's consistent. Our original function was x squared. The derivative we got was 2x. It follows the power rule, and all power functions will work under the same rule. We haven't noticed that I didn't actually prove this to you that it works for all of them, but notice that it will work in every example so far. And let's look at more examples in the next slide.